Check out. Number 5, we have two functions here. They give us f of x is 1 over x, and g of x here is 4x over 1 plus 4x squared. And they tell us in part A here, find the absolute maximum value of g on the open interval 0 to infinity if it exists, and then find the absolute minimum value of g on the open interval 0 to infinity if it exists, and justify your answers. So we're dealing with just the g function only here. So in order to find maximums and minimums on open intervals, etc. Ultimately, we don't have any endpoints to consider here, so the candidate test is not necessarily helpful here because we need to figure out the other critical points because there are no endpoints, so therefore we could do stationary points, singular points, any points where the derivative equals 0, derivative does not exist. So ultimately, if we find the derivative here, let's see, it's a quotient rule problem. We do the bottom times the derivative of the top, top times the derivative of the bottom, all over the bottom squared, 1 plus 4x all squared. And we do the math on top, we get 4 plus 16x squared minus 32x squared, which ultimately will give us 4 minus 16x squared on top, 1 plus 4x all squared on the bottom. Alright, so ultimately to find these critical points, we know that this derivative will equal 0 if the top equals 0. Dash, I missed something.
Isn't the 4x plus x squared on the bottom?
Oh, yep. Take that, so that's squared also. Alright, good. Alright, and so ultimately we know that the top equaling 0 would make the derivative equal 0. So if we subtract and divide, we end up with a quarter over here. So we get x equals plus and minus a half. We only need to worry about the positive one though because they told us the interval here is 0 to infinity. So that would be one critical point. The other critical points would be if the derivative doesn't exist, which would be here. And the question is if I were to put any number in here and I squared it, and then I multiplied it by 4 and added 1 to it, and then I squared it again, is there any chance that this could ever be 0 here? Remember, the only way that this could be 0 is if this whole thing equaled -1, true? And if I squared something and multiplied it by 4, could it ever equal -1? So really the only critical point then is x equals a half. So let's test it. So if we do our first derivative test here with 1/2, and we're going to need to put something in here that's between 0, remember, because 0 is a boundary for us too, because we're going from 0 to infinity. So you can't put something negative in there because that's not going to help with our test. But ultimately, if I put, say, a quarter in there, for instance, if I put a quarter in here, I'd get a quarter squared, which would be quarter squared would be 1/16 times 16 would be 1, so it would be 4 minus 1 on top, we get a positive. And on the bottom we get always positive, so it's positive over positive, which would be positive. And then from there, if we put say a 1 in there, for instance, we'd get 4 minus 16 on top, positive on the bottom, so that would be negative. And so what does that indicate for 1/2? It would be a maximum point. Okay. So, and keep in mind that we're from 0 to 1/2 we're increasing, 1/2 to infinity we're decreasing. So there are no other critical points here. Alright, and with that, keep in mind the question is find the absolute maximum value. Okay. So we actually need a value here. We found the location half, so we need to ultimately put that g of 1/2 to work for us here. So we'll put a 1/2 into our function. And if we do that, we get 2 on top. On the bottom we'd have yeah, 1 plus 1 would be 2. So ultimately the value itself would be 1. Okay. So if we find the maximum value, that's 1. Alright, and then the other part here is how about the minimum value? If this starts at 0 here, and at 0 something, and we know that the actual value here, if 0 was included, it'd be 0 over 1. Ultimately it'd be 0, 0. Goes from the origin if 0 was included. So it's increasing until we get to 1/2, 1. And then what happens after we go from 1/2, 1 to the right? It decreases for how long? decreases for the rest of the x line, which ultimately means is there a minimum here? So there is no minimum. And again, when you think about it graphically, that could be one of two things. I mean, it could look something like this. You know, it could just go down forever. Okay. Or could it also do something like this? Could it maybe do that and have x equals 0 be a horizontal asymptote? It's going to approach. It could very well approach 0, but does it ever actually get to 0? Okay. So therefore, no minimum. All right. So a point breakdown for this one was as follows. If you found the derivative correctly, you get 2 points. So if you found that, use the quotient rule problem with 2 points, which seems pretty generous, but that's what they gave. Finding the critical point of 1/2 was another point. Your answers and justifications, keep in mind the justifications is our first derivative test here. So your answer here, 1 for the maximum value, and no minimum value. So a point for these two parts here, and then another point for the justification, which is ultimately your first derivative test. Okay, questions on that one? All right, so 5 points altogether for that one, which is pretty nice. And then in part B, it asks us to find the area of the unbounded region in the first quadrant to the right of the vertical line x equals 1, below the graph of f and above the graph of g. Okay. So if we set up our integral, we're going from essentially 1 to infinity, so anything to the right of the vertical line x equals 1, of the above the graph of g, below the graph of f, so ultimately it'd be f of x minus g of x. Alright, and we notice here, first thing we should notice here is that we have an improper integral, because we have an infinity as one of our limits. So we first write the limit as b approaches infinity, of 1 to b, of our f of x function, which is 1 over x, minus the other function, 4x over 1 plus 4x squared dx. So ultimately that would be our integral setup. Okay. And if you do that correctly, you get 1 point. Alright, and then from there, we'll anti-differentiate. So we know that this is natural log of absolute value of x. For this one, that one's no problem. This one, however, if we're going to integrate this one, we will need to use u substitution, because we ultimately have 1 over 4x squared, and then we have 4x here, which the derivative of this is clearly going to be a factor of 4x here. So if we do our u substitution somewhere, if we go u equals 1 plus 4x squared, our du would be 8x dx. But we have a 4x dx to get rid of, so if we did a half du, it was 4x dx. So when we integrate here, we're going to have 1/2 out in front. We're going to have 1 over u du. So we're replacing the 1 over 1 plus 4x squared with u. And du is 1/2 du is the replacement for the 4x dx part. And so we'd ultimately end up with a natural log of absolute value of u, which would be natural log of absolute value of 1 plus 4x squared. And keep in mind we don't really need the absolute value for this because this can't be negative. So at this point, we can write a half natural log of 1 plus 4x squared. Alright, 1 point for that part, actually 2 points for that part. 2 points for anti-differentiating correctly. Alright, and then the final part is for coming up with an answer for that. So we got, keep in mind that we're evaluating that on 1 and b. So if we do ln b minus 1/2 ln 1 plus 4 b squared, that'll be that part, minus ln 1, 1/2 ln 5. So put a 1 in here, we're going to get 1 plus 4 in the parentheses. So, alright, and again, remember the only way you can evaluate this is if we look at the limit as b approaches 0 here. Alright, so in this case, What do we got going here? If we go b approaches 0 here, or excuse me, b approaches infinity here, we ultimately have our natural log of infinity, and then this one is going to be minus, really also natural log of infinity. Okay, so it's essentially it's an infinity minus infinity case. So what I would suggest is if we rewrite this whole operation, we might be able to put this in a nicer form, and then maybe evaluate. Because ultimately this infinity minus infinity is indeterminate, so we can't really tell whether that's infinity or whether that's a value or whatever. But ultimately, if we have natural log here, if we put the 1/2 up on the power up here, we could put these two natural logs together because we have a natural log of a subtraction. So that we could write it as ln b, and then it would be square root of 1 plus 4b squared. If we put that all into one expression, and again we're taking that 1/2 and put it on the argument here. And we're putting it together as a division because it's a subtraction here. And then we're subtracting that, and we can put these two together also. And in this case, we'd have natural log of 1. And keep in mind the natural log of 1 is just 0, so we don't really even need to deal with that. But we can ultimately just have natural log of 5 to the 1/2, or radical 5, if you will. And once again, now we have another subtraction here, so we could write this all in one sentence. We'd have b, and then did I miss one? Oh, you're right, it's minus, minus, thank you. Plus, so that would be b radical 5, and then on the bottom be 1 plus 4b squared. When we're plus sign, we'd be multiplying the two arguments together. Alright, so now the next part then is now can we evaluate it with the limit as b approaches infinity? So can we come up with an answer for this? Is the question. Well, think about how this is going to behave if we have b and we have radical 5 here, and we have radical 1 over 4b squared here. Remember, at infinity, as b approaches infinity, this function is the one going to have any relevance for us? Okay, and ultimately, so this function under here is going to essentially behave like radical 4b squared, isn't it? So what's it really going to behave like? It's really going to behave like 2b. And what's this function going to behave like? Radical 5b. Okay. And so ultimately, what am I going to get here? The b's are going to cancel out and be left with the natural log of radical 5 over 2. So again, just going to think about what is this going to be at infinity. It's ultimately going to behave like radical 5 over 2 because, again, is this something that, since we had an infinity over infinity case here, could we use L'Hopital's rule here too, possibly, to determine that? Good. Don't necessarily have to because ultimately your work is good there on that. And I guess that's it. So, other points here on this one where I guess just one last point is just getting the final answer. Okay. So, everything else is again integral setup, finding the two antiderivatives. And like I said, arguably the most difficult part here, I guess, the algebra part of getting that to finding the correct limit, which is worth 1 out of the 9. Questions on any part of that one? All right. So let's take a look at number 6. Number 6, we have a Maclaurin series. See, it's alternating. And there's one thing that when we do this first problem, it's asking us for the interval of convergence here. We know that ultimately in any problem like this where we have something in x here, and we're looking for the interval of convergence, we know that whatever we raise this power to, this nth power, Okay, that stuff in here needs to be between -1 and 1. Okay? And so in the past we've just done absolute value of 2x is equal to less than 1. Okay, because keep in mind that this is going to ultimately grow if this is not between -1 and 1. Okay? If I put something in here that was not between -1 and 1 and I raise it to a power, it's going to grow. Okay? So therefore there's not going to be any convergence. So we know that that has to be a fraction in order to converge. And ultimately we know that when we rewrite that into the other form, we write it like that, and then if we divide, we get -1/2 to 1/2. Alright, and so ultimately that's going to be our interval of convergence. Alright, and with that, we know that there's another issue though underlying, and that's the fact that we have to test the endpoints here and see if the endpoints converge or not. Now before we do that, there is some points here that I think we'd miss if we didn't show the work for this. Ultimately, what they give points for setting up the ratio test on this. Okay? And so even though our book didn't necessarily do that, we're going to revisit this just to make sure that we're clear. If we try to do the ratio test here with the arguments here, we're going to have n+1 and then n+1 minus 1. And then we're going to divide that by our original here, which would be n-1, and then 2x to the n. Okay. This is ultimately showing us with the ratio test that we can get from this to this right here. So keep in mind that when we have these two things to the one power bigger than the other, that we're ultimately going to just have that gone and that gone. And then these are going to be, this is n+1, this is just n then. And I know that as I take my limit as n approaches infinity, what do I know about n-1 over n? That's just 1. And so ultimately what do I get with the ratio test? I get 2x. Okay? And again, that has to be less than 1. And they actually gave a point for the ratio test part for that. So, like I said, in our book, they didn't demand that you do that, but on the AP test, okay, they're going to give you a point for showing that. So, if they ask you for the interval of convergence, okay, I haven't seen any that are not the ratio test. So, if you do your ratio test, put your n+1s in there, divided by the original, and just show that the limit of that as n approaches infinity. Okay, we know that that has to be less than 1 in order to converge. Okay, and so that's ultimately I guess the more mathematical way to show that this is true in this problem. Okay. So like I said, if you show that, you get 1 point. If you evaluate the limit, in other words, you get to this point here, okay, then you get another point. And if you find the interval of convergence, you get yet another point. So if you get -1/2 to 1/2 is your interval of convergence, you get another point, so 3 so far. And like I said, the other issue is whether we're going to make either one of those or equal to's. So if we put our -1/2 into our original, we're going to have -1 to the n, -1 to the n over n-1. And if I do -1 to the n times -1 to the n, that's -1 to the 2n, which ultimately is -1 to the 2 to the n, which is again in turn is just 1. And ultimately we have 1 over n-1. Now what do we know about that? 1 over n-1, isn't that p series? So if it's p series, does it converge or diverge? P is 1 or less, right? P is 1 or less, it's going to diverge. So therefore we will not make an or equal to on that one. If we put a half in there, we're going to get -1 to the n over n-1. And ultimately, because keep in mind that when we put a half in here, we're going to get just 1 to the n, which is 1. So what do we notice about this one? This one is p series, kind of, but it's alternating. And as long as it's alternating and it goes to 0, what do we know about this one? This one what? This one converges. So if it's alternating, that makes it a different story altogether. So if that one converges, then we'll have our final answer with a or equal to on the 1/2. And ultimately, if we consider both endpoints, if we did both endpoints and found an answer for both of those, we get a point. And then finally, the last point is essentially for having that, having the or equal to on the 1/2, recognizing that that does diverge, or converge, I mean. Questions on that one? Okay, so 5 points for that part. Part B is worth 4, obviously, and what we're asked to do here is to show that this this y equals f of x function that we were given up top, which is ultimately defined as a summation, okay, is a solution to the differential equation. And the differential equation that we have is x y prime minus y equals 4x squared, and then 1 plus 2x. Now, keep in mind that I guess one general strategy here would be to recognize that if they want us to show that that y equals f of x is a solution to this differential equation, okay, that this in this sentence being true with our particular y, which is again the sequence that they gave us up top, or the series they gave us up top. Okay, I guess my best bet here, I guess, if they want us to show that this is a true sentence using the y that we have, is to kind of treat it as an identity and just see if we can show that that the one side equals the other. Okay, so I guess that would be probably my advice in terms of what approach to use here. And so, knowing that we know y, and keep in mind that y is, if we were to go back up here, keep in mind this is y right here. This is our f of x, which is equal to y. Okay, if we were to just start generating some terms here, if we put a 2 in for n, we're going to have 2x to the 2 over 2 minus 1. And so we're going to have ultimately 4x squared over 1. Okay, would be our first term. If we were to put a 3 in there, we're going to get 2x to the third. That's going to be 8x cubed over 2. 8x cubed over 2 is going to be 4x cubed. Okay. And again, so just let's go through and we're going to list a few of these. If we do a 4 in there, we're going to get 16x to the fourth over 3. So 16x to the fourth over 3. And ultimately, again, we can just continue that on for however many we need. Okay. So ultimately, again, recognizing that that is y. And remember, that's part of our expression here. That's this part. What else do we need in our expression? We need a y prime. So if we did y prime is going to be the derivative of this. So we could write 8x here. We could write 12x squared here. We could write 64x cubed over 3 here. All right. And again, continue that for however many terms we want to show. But ultimately, that right there is the derivative. Okay. And keep in mind, we're trying to get an expression that is this and show it's equal to this. Okay. So ultimately, I have y and I have y prime. All I need now, if I had an xy prime, that would be the term out in front. So my xy prime would just be y prime all multiplied by x. So we get 8x squared plus 12x cubed plus 64x to the fourth over 3. Run out of space here, but ultimately that would be an expression for xy. And then what would we need to do with that to get the final answer on the left-hand side? Take this expression and subtract what? Subtract y. Okay. So let's do that here. So if I take my xy prime expression and I subtract the y expression, then xy prime minus y is going to be ultimately 8x squared, and these are all like terms, notice. So if I'm going to go 8x squared minus 4x squared, I'm going to get 4x squared. 12x squared, or cubed minus 4x cubed is going to be minus or plus 8x cubed. 64 minus 16 is going to be 48x to the fourth over 3. 48 over 3 is 16. Alright, so now keep in mind though that what they want us to do is to show that, and this is also, remember, an infinite list here, and they want us to show that that's equal to 4x squared over 1 plus 2x. Well, question is, how do we show that this, okay, which is an infinitely long string of terms, equals this? Okay. So we can see that that one thing we have here is very similar to what we have here. And you should also notice that if I have 4, 8, 16, and that pattern continues, what do these terms all have in common? They all have 4x squared in common, don't they? And so what would I be left with? I'd have 1 plus 2x plus 4x squared plus and so on. Okay. All right, and here's the key to the whole thing, and this is where the last point comes in. Ultimately, I guess like I said, the hardest part to visualize is this last part. Okay, what do we have right here? What kind of, this is a, keep in mind, we need to go from some kind of series to some kind of finite answer here, right? Okay, so what do we got in here? What kind of series is it? What kind of series would we hope it was? Yeah, if it's geometric, we might be in good shape here because we can find the answer to this, can't we? The sum of this is the answer, true? Okay, and what is the sum of this? It's a over 1 minus r. And what's our r? Yeah, our r is actually, you know what, I missed a. This was, you know, these are all supposed to be pluses and minuses, sorry. These first terms are minuses. I forgot this was alternating. So this is in minus, minus, minus here. So ultimately it'd be negative 2x. If it wasn't negative 2x, then it wouldn't have worked out very nicely, right? So again, remember this right here, what I have in parentheses, is this. Okay? It's a over 1 minus r. And r being negative 2x here, okay, would ultimately give us 1 plus 2x on the bottom times 4x squared. And what do I notice about the left and right hand sides now? Yeah, they're equal, aren't they? Okay. So that one took a little bit of pretty tricky visualization. If you could do that, hopefully. Keep in mind, I guess, in general, you know, if we're trying to say that this infinite series, okay, is some finite answer, okay, then hopefully we can recognize it as geometric, because really the geometric one is the only one that we can actually find a sum for at this point. So, like I said, that's kind of the insight that you'd want to try to think of if you had a problem like that again, where we know we had to turn some geometric series into some finite equation. Okay. And it works out nice once you see it. Like I said, whether you got that right or not on your own would be, you know, I guess will remain to be seen. But like I said, more experience that we have of seeing something like that, the better. So ultimately, again, just recognizing the fact that we need to essentially show that this identity was true using the y that we had here. If you found your y prime statement, you got a point for that. If you found the xy prime statement, you got a point for that. And if you wrote the xy prime minus y statement, you got 3 for that. So really the hardest part of it, which is again recognizing the geometric series in there, okay, that was only worth 1 out of the 4. So if you did recognize that and showed the final part, you get that one final point there. Okay. Questions on any part of part B?